Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to look at diagonalization. So in this topic, we will see that we can write a symmetric matrix as the product of an orthogonal matrix, a diagonal matrix, and the transpose of that orthogonal matrix. And this process will be described as diagonalization. You will see that this allows us to examine how the matrix actually affects vectors in the vector space, and we'll look at a few examples and consider some applications. Now, given a symmetric matrix, A mapping Rn to Rn, therefore it is self-adjoint, and consequently there must exist an orthonormal basis of eigenvectors. Now, those eigenvectors p1 through pn correspond with eigenvalues lambda 1 through lambda n. Now, we know this is true because we already saw that for a symmetric, or more generally a self-adjoint linear operator, eigenvectors corresponding to different eigenvalues are already orthogonal, and if we have found more than one eigenvector for a given eigenvalue, then we can also apply Gram-Schmidt to create an orthonormal basis for that eigenspace. All right, so we have these n eigenvectors that are orthogonal and normalized, and they correspond. Thus, A applied to the kth eigenvector is equal to lambda k times that eigenvector for all k going from 1 to n. We can now define the matrix P consisting of these eigenvectors. Now, this is going to be an orthogonal matrix, that is a isometric matrix that is real, for the columns form an orthonormal basis in Rn. Incidentally, so do the rows. And you will recall that isometric matrices on real finite dimensional vector spaces are called orthogonal matrices. Consequently, the inverse of an orthogonal matrix is the transpose. And this is in fact the only safe time one can actually guaranteed calculate the inverse with no issue of numerical instability. Now, given a vector u, if we want to find scalars alpha 1 through alpha n such that this linear combination of this orthonormal basis equals the target vector u, then normally we would have to solve this system of linear equations for the unknown vector alpha. However, because P is orthogonal, all we have to do is multiply u by the transpose of P. That is something that can be done without any issue of numerical instability. Now, consequently, given that we have found the coefficients that allow us to write u as a linear combination of our orthonormal basis, then A applied to u, or A times u, is equal to A multiplied by this linear combination of our orthonormal vectors. But A is linear, and thus we have that the operator applied to a linear combination of orthonormal vectors is equal to that same linear combination of the operator applied to each of the orthonormal vectors. But all of those vectors are eigenvectors, and so consequently A applied to the kth eigenvector is equal to lambda sub k times the kth eigenvector. Okay, so that's actually quite nice. You will remember the definition of matrix vector multiplication, and looking at this, the right-hand side is simply a linear combination of the eigenvectors. All right, the right-hand side is actually just the matrix P, which is the eigenvectors multiplied by a vector that is simply the scalar multiples lambda 1 times alpha 1, lambda 2, alpha 2, etc. up until lambda n times alpha n. So therefore, A times U is just P times this vector here, where the alphas were found by multiplying U by the transpose of the matrix P. Also, however, we can actually calculate this vector by multiplying the alpha vector by this particular diagonal matrix. That is, the diagonal matrix that has the eigenvalues on the diagonal. So multiplying that diagonal matrix times the alpha vector gives us the vector we see in the center. Therefore, A times U is equal to P times this diagonal matrix times the alpha vector. But wait a second, the alpha vector was found simply by multiplying the vector U by the transpose of P. So consequently, if A times U is equal to this product of three matrices times U, then the matrix A must be equal to the product of the three matrices. So a consequence of this equation being true for every vector U is that every symmetric matrix can be written as the product of an orthogonal matrix of normalized eigenvectors, a diagonal matrix of the corresponding eigenvalues, and the transpose of that orthogonal matrix. So A is equal to an orthogonal matrix times a diagonal matrix times the transpose. This process is called diagonalization, and the eigenvalues give you how much the matrix affects each of the corresponding eigenvectors. Note that this product is symmetric. So if D is the diagonal matrix of eigenvalues, then the transpose of that product is equal to the transpose of each of the individual entries in the reverse order. The transpose of the transpose is equal to the matrix itself. The transpose of a diagonal matrix is equal to itself. So yes, we see that the transpose of the left-hand side equals the right-hand side, equals itself actually. Thus, in order to create these matrices, given a symmetric matrix, find all the eigenvalues for that matrix. For each eigenvalue, find a linearly independent basis for that eigenspace. That basis is not necessarily guaranteed to be orthogonal, so apply the Gram-Schmidt algorithm to create an orthonormal basis. Of course, if there's just one vector, or if the eigenspace is one-dimensional, you just have to normalize that eigenvector. This is going to create n orthonormal vectors P1 through Pn. From this, we will define the orthogonal matrix P. From this, we can let lambda k be the eigenvalue corresponding to the eigenvector P sub k, and define the diagonal matrix to be the diagonal matrix of these n eigenvalues, some of which may be repeated. Note that if a matrix has n linearly independent eigenvectors but is not symmetric, then the matrix P will not be orthogonal. So, for example, if the matrix has n different eigenvalues, then the eigenvectors corresponding to those n different values will be linearly independent of each other. The problem is, because the matrix is not symmetric, the matrix P will not be orthogonal. Thus, calculating the inverse will necessarily require you to either apply a numerically unstable algorithm to calculate the inverse so that you can write the matrix A applied to U as P times the diagonal matrix times the inverse times the vector U. Alternatively, you can use Gaussian elimination and backward substitution or some other matrix decomposition to solve P times alpha is equal to U for each new U. Having found the alpha vector in either case, you calculate P times D times alpha. Now, because the eigenvectors are not orthogonal to each other, you cannot rely that each will individually express the entire effect of the linear operator in the direction of the eigenvector in question. So let us calculate the diagonalization of this matrix A. Here the matrix is 0.08, negative 1.44, negative 1.44, 0.92, and it is symmetric. First, we calculate the determinant of lambda I minus this matrix. Now, that for a 2 by 2 matrix is just a product of the diagonal entries minus the product of the off-diagonal entries. So this would be lambda minus 0.08 times lambda minus 0.92. Subtracted from that is 1.44 squared. Now, fortunately, this simplifies to lambda plus 1, lambda minus 2, and therefore the two eigenvalues are lambda equals negative 1 and lambda equals 2, the roots of this polynomial. All right, now to find the null space for lambda equals negative 1, I substitute lambda equals negative 1 into the matrix lambda I minus A. So negative I minus A is the matrix that we see here. Now we are looking for the null space, so we solve the homogeneous system of linear equations, and incidentally, the second row is indeed a scalar multiple of the first, and so this is row equivalent to this matrix here. Therefore, alpha 2 is a free variable, and therefore we can determine that alpha 1 is 4/3 times alpha 2. And if we normalize that vector there, we get that the first normalized vector is 0.8, 0.6. Next, to find a basis for the null space when lambda is equal to 2, we calculate 2 times the identity matrix minus A, which is this matrix here. Once again, we apply Gaussian elimination to eliminate the second row, and in fact the second row is a scalar multiple of the first. It has to be because the null space cannot be just the zero vector. So consequently, once again, alpha 2 is free and alpha 1 is equal to negative 0.75 or negative 3/4 times alpha 2. Once again, we can normalize this vector to get that the second normalized vector is negative 0.6, 0.8. And as you can see, that is orthogonal to the first normalized vector. Thus, the matrix P is created by taking these two normalized vectors and creating the matrix. And the diagonal matrix is the eigenvalue corresponding to the first vector, which is -1, and the eigenvector value corresponding to the second eigenvector, which is 2. So if you were to actually calculate P times this diagonal matrix times P transpose, you would get back the original matrix A. What this tells you, however, is that the effect of this matrix is to, in the direction of P2, to scale by a factor of 2, whereas in the direction of P1, it's actually a reflection in the axis defined by the vector P2. Okay, so to find a diagonal decomposition of this matrix here, the first step we do is calculate the determinant of this matrix lambda I minus A. So that is, of course, going to be the product of the diagonal entries minus 16 minus 16 plus lambda minus 10 times 16 minus lambda minus 13 times 4 minus lambda minus 13 all times 6. Now, this rather ugly polynomial can actually be simplified to the following: lambda minus 9 squared times lambda minus 18. Thus, 9 is one eigenvalue with multiplicity 2, and 18 is the other eigenvalue. So let us substitute lambda equals 9 into that equation and solve the homogeneous system of linear equations to find a basis for the null space. The basis for the null space will be the eigenvectors. All right, so taking a look at this, well, without much work, we see that it's row equivalent to this matrix here. Therefore, alpha 2 and alpha 3 are free variables, and alpha 1 depends on those two. So those are our two vectors, eigenvectors, but they are not linearly independent, but that's okay because they belong to the same eigenvalue, lambda equals 9. Consequently, we can apply Gram-Schmidt in order to produce a an orthonormal basis. Now, with a little bit of stress and pain, we can find that that is one normalized eigenvector, and this is the other orthogonal and normalized eigenvector. All right, next let's go to 18. Substitute 18 into that matrix, lambda equals 18 into that matrix, and we get the following. Now, once again, applying row echelon form, we get that that is row equivalent to the following matrix. That says that this is an eigenvector for the eigenvalue lambda equals 18. We don't have to worry about Gram-Schmidt anymore because 18 has only one eigenvector, and therefore that eigenvector must be orthogonal to all other eigenvectors. However, normalizing it, we get this vector here. Okay, so thus for this matrix here, we have the diagonalization with the P matrix shown on the left. As you can see, the three columns are normalized and they are orthogonal to each other. And D is the diagonal matrix with the eigenvalues on the diagonal. Note that the first eigenvalue corresponds to the eigenvalue of the first vector, so does the second, and the third eigenvalue, 18, corresponds to the eigenvector in the third column. Therefore, the matrix A is equal to P times that diagonal times the transpose of P. Now, consider a mass that has multiple stresses placed on it. The principal directions of the stress can be found by finding the eigenvalues and eigenvectors of the corresponding stress tensor. Now here's an interesting image that uses polarized light to demonstrate where the different stresses occur in this protractor when certain pressures are placed upon it. Often stresses locally can be modeled only by focusing on the largest of these eigenvalues and its corresponding eigenvector. Also, given a load-bearing structure, when the structure is placed under a load, the structure not only bears the load but also buckles under that load, and thus changing the shape and therefore the characteristics thereof. This is the relative effect of buckling can be modeled by a symmetric tridiagonal matrix. And again, each point affects the points nearest to it, and the effect on one point equals the effect on the other, hence the symmetry. Following this topic, you now understand that a symmetric matrix can be written as an orthogonal matrix times the diagonal matrix times the transpose of that orthogonal matrix. You understand that this allows you to focus on the effects of the matrix relative to the eigenvectors and the directions in which they point. You've seen two examples of this decomposition and looked at a few applications of eigenvectors where the matrices are indeed symmetric. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!